Okay, so we're going to wrap up section 4.2 here. This is the last couple that we need to look at. We got one example, finding the max and mins of a trig function. So we're going to say find the max and min of our function f of x, which is equal to sine of x plus cosine squared of x. And that's going to be on the interval 0 to 2. Sorry, 0 to 2 pi. So we got our endpoints. They told us 0 to 2 pi is the endpoints of the interval. So we'll get 0 and 2 pi. We got to include those. We're going to look at the first derivative, which will be derivative of sinus cosine. This one, the chain rule applies. 2 is sort of the outer function, so we bring the 2 down, leave the inner part, which is the cosine part, alone. Multiply it by the derivative of cosine, which is negative sine. And we get f prime of x is cosine of x minus 2 cosine of x sine of x. This won't be undefined anywhere, so we're going to set it equal to 0 and try to solve it. So we'll factor the cosine out. We'll set these in equal to 0. So cosine of x equals 0, or 1 minus 2 sine of x is equal to 0. If we think about our unit circle, cosine of x is the x values. The x values on the unit circle are 0 here and here. So that's going to be cosine of x equals 0 will happen at x equals pi over 2 and the x equals 3 pi over 2. Because those points on the unit circle have x value of 0. Now for this one, we're going to solve it. So we get 1/2 is sine of x. So sine of x is the y value of the point. It's at 1/2, which is here and here. And that will occur at x equals pi over 6 and x equals 5 pi over 6. So if you don't have your unit circle memorized, go through and memorize it to get your values. So we have 4 critical points to check. Pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. So these are all critical points. Okay, so we're going to take these and we're going to plug them in. Each of these x values, we're going to plug them into the original function. Our original function is sine of x plus cosine of x squared. All right, so let's see what we get back. 0 gives us back 1. We put in 2 pi. That gives us back 1. We put in pi over 2, gives us back 1. 3 pi over 2 gives us back negative 1. Pi over 6 gives me back 1.25. And 5 pi over 6 also gives me back 1.25. So negative 1 is our minimum value. This right here is our absolute minimum. And 1.25, even though it turns up twice, 1.25 is the maximum value. So the smallest y value that we get on the interval is negative 1. The largest y value we get back is 1.25. Okay, so that wraps up the sort of using endpoints and critical points to find the maximum or minimum values on intervals. The next example we're going to look at is going to be over something called Rolle's theorem. So this will kind of wrap stuff up. So we're going to assume f of x is continuous on a to b. And differentiable on open interval a to b if the starting point's y value f of a equals the stopping point's y value of the interval, then there exists a number c between a and b such that f prime of c equals 0. So basically what this is saying is if you have a continuous function and we have a starting point here that's from A and the stopping point's the same height at B, if I start going, say, up, at some point I'm going to have to turn around to reach B, and when I turn around that'll create a horizontal tangent line, which will mean the first derivative is 0. If I maybe start out heading down, eventually if I'm going to reach B again, I have to turn back up to reach B. Sorry, that's supposed to be an A. And when I turn back up, that'll create a horizontal tangent line down there. And horizontal tangent lines have first derivative 0. So that's basically how this theorem works. And then our last example we're going to take a look at. I know that there's an example 8 in the book, but it's a little more involved, and I think we're going to not really look at it. It's a little more involved than they probably would ask you on AP test. But if you want to read through it, you certainly can. We're going to say, for this example, you know, we'll just do example 8 also. We'll do them both. We want to verify Rolle's theorem for the function f of x equals x to the fourth minus x squared on the interval -2 up to 2. So this is a polynomial, so we know it's continuous and differentiable. So we'll say f of x is a polynomial. So is continuous on -2 to 2 and differentiable on -2 up to 2. We need to show f of a equals f of b, so we need to show f of -2 equals f of positive 2. F of -2 equals -2 to the fourth minus -2 squared, which is 16 minus 4, which is 12. F of positive 2 equals 2 to the fourth minus 2 squared, which is 16 minus 4, which is also equal to 12. So we have f of -2 equals f of positive 2. And therefore, there will exist a c such that the first derivative is 0, and that c value will be between -2 and 2. So to verify this, we want to take the derivative of this and show that one of the zeros is between -2 and 2. And if we can do that, we'll have verified that stuff that we want to prove is working. So here's our first derivative. Let's see. Let's try to find the zeros of that. So let me factor out a 2x. So I get zeros at x equals 0, x equals 1, and x equals -1. Really, we only needed one of these. We got 3 of them. So we only needed to show that there was one in between. We got 3 points where that is, where f prime is 0. So this is verified. We showed it. Okay, and then let's basically said, okay, all the setup was there. Then show that there exists a c between a and b such that f prime of c is 0. Well, we could use x equals 0. 0 is in between. Could say 0 is in -2 to 2, and f prime of 0 is 0, so it's verified. We could have used 1. We could have also used -1 because we had three candidates that are within that region. But to verify the theorem, we only need 1, so I just chose 0 because it was the way I wrote it there. So, all right, last one. Let's get some space to work on stuff here. We're going to look at example 8. So we want to show f of x equals x cubed plus 9x minus 4 has precisely one real root. Okay, so this is continuous, so we're going to use the intermediate value theorem first, and I'm going to say f of 0 is equal to -4. So if I put 0 in for the x's, I get -4 back. F of 1, if I put 1 in for the x's, I get 6 back. So f of 0 is -4, f of 1 is 6. F of x is continuous on -4 up to 6. So by the intermediate value theorem, there exists at least one c in -4, sorry, be open bracket, -4 up to 6, such that f of c equals 0. So since 0 is between -4 and 6, whoops, I'm messed this up quite a bit here. Let me fix it. So, okay, mistake I made is I put the y values down here instead of the x values. So, you go through and fix that. -4 and 6 are the y values. The intermediate value theorem bases itself about the x values for the intervals. So I should say f of x is continuous on 0 up to 1 because that's the x values I'm dealing with. By the intermediate value theorem, there exists at least one c in open interval 0 to 1 such that f of c equals 0. And we're going to note that -4 less than or equal to 0 less than or equal to 6. So 0 is between -4 and 6. So the intermediate value theorem guarantees me that there is some c like that. Doesn't guarantee that there's one. It guarantees me that there's at least one 0 like that. So we're going to suppose that there is a second 0 or second root, we'll say at x equals d, such that f of d equals 0 also. So if we can prove that this causes a contradiction, then, so if supposing there's a second root that also equals 0, if that causes a contradiction, then we'll be guaranteed that there can be only one root, and it will occur where the f of c equals 0 is up here. So f of x is still a polynomial. We're looking at the region 0 to 1. It's continuous there. It's differentiable there. And we have f of c equals f of d, and they both equal 0. And if we can show that that's saying that there is a second one, if we can show that this causes a contradiction, then we'll have shown that there's that there could only be one. So by Rolle's theorem, because we're continuous, we're differentiable, and we have the endpoints of whatever this interval is, we have the endpoints equal 0. So by Rolle's theorem, there is some number in 0 up to 1, because this f of d, if this is a root also, the second root is going to have to be in the same 0 to 1. So by Rolle's theorem, there's a second number in that 0 to 1 such that the derivative at that second number, I'll call it, let's say k. We'll call it k. So that such that the derivative at that value is 0. So we claim if there's a second root in 0 to 1, then there has to be some k value in 0 to 1 such that the first derivative of that k value is 0. So let's see what the first derivative of our function actually is and see if there's a contradiction. Well, f prime of x equals the 3x squared plus 9. That's it. 3x squared plus 9, regardless of what you put in, this is always, so if I put in an x that's negative, it gets squared, so it goes positive. If I put in 0, 0 gets squared, it's still 0, but I get a 0 plus 9, so it's 9. If I input a positive, it gets squared, it gets multiplied by 3, and then added to 9. This is always greater or equal to 9. The first derivative is always greater than or equal to 9 for all x's in the interval 0 to 1. So this is a contradiction. As Rolle's theorem says, Rolle's theorem states that there is a k in 0 to 1 such that f prime of k is 0. Well, there can't be a k like that because f prime of x is 3x squared plus 9, which is always bigger than or equal to 9. So it can never be 0 because it's always bigger than or equal to 9, and 0 is never bigger than 9. So we get a contradiction. So there is no second root. So f of x has precisely one root. There cannot be a second root because it contradicts with Rolle's theorem. So f of x has precisely one root. And we proved it. So that's going to wrap it up. That proof's a little tricky. If they asked that on an AP test, that would be one of the challenge AP questions. This one I think is kind of rough. Wraps the section up though, so we'll stop there.